Namaskar, I am Dan Gaude, Assistant Professor in Mathematics, uh, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the equivalence class from the group theory of algebra of MSc first semester first. Definition for equivalence class. Let X be a G set because group G action on a X. Each equivalence class produced by an equivalence relation defined by on X described in is called the orbit of X under G. The equivalence class containing X belongs to X is the orbit of X, and we denote it by Xg. Xg is equal to Y belongs to X, so that X equivalent to Y is equal to Y belongs to X is equal to, so that X is equal to Yg for some G belongs to G. A relation between the orbit Xg and the subgroup Gx in a G set X as follows. Next theorem. Let X be any G set, then the coordinate of Xg is equal to index of G over Gx. Then prove that coordinate of Xg is equal to index of G in Gx for any X belongs to X. For proof, picks up any X belongs to X. Let R denote the collection of all right cosets of the subgroup Gx in G. We will show that R is equipotent with the set Xg. Now Y belongs to Xg, Y is equivalent to X, Y is equal to Xg for G, some G belongs to G. Define phi from Xg to R by phi of Y is equal to Gxg, where Y is equal to Xg, G belongs to G. We have to prove that phi is well defined. Suppose that y1 is equal to y2 in xg. Then y1 is equal to xg1, y2 is equal to xg2. Therefore, y1 is equal to y2. This implies that xg1 is equal to xg2. This implies that xg1 g1 inverse is equal to xg2 g1 inverse. And by associativity, x g1 g1 inverse is equal to x g2 g1 inverse. X multiply E is equal to x multiply g2 g1 inverse. Therefore, x is equal to x g2 g1 inverse, and g2 g1 inverse belongs to gx, and gx g1 is equal to gx g2. Therefore, phi of y1 is equal to phi of y2, and this shows that phi is well-defined mapping. Now we have to prove that phi is 1, 1. Let phi of y1 is equal to phi of y2 for some y1, y2 belongs to x. Therefore, phi of y1 is equal to gx g1. For some y1 is equal to xg1, and phi of y2 is equal to gx g2 for y2 is equal to xg2. Thus, phi of y1 is equal to phi of y2. Therefore, gx g1 is equal to gx g2. g1 g2 inverse belongs to gx. X g1 g2 inverse is equal to x. X g1 g2 inverse is equal to x. Therefore, x g1 is equal to x g2. Therefore, y1 is equal to y1 to y2. This shows that phi is 1, 1. Now we have to prove that phi is on 2. Let gx g belongs to R. this implies that G belongs to G. For this G, consider the element y belongs to X defined by y is equal to xg. Then phi of y is equal to gxg. This shows that phi is onto. As phi is well defined, phi is on 1, phi is on 2. This is xg is equal to coordinate of r. Coordinate of xg is equal to coordinate of r, where coordinate of r is equal to number of right coset of gx in g, that is index of g in gx, and this is proved that coordinate of xg is equal to index of g in gx for all x belongs to x. Corollary. Next corollary. Let G be a finite group and let X be a finite G set. Then coordinate of G is equal to coordinate of Xg multiply coordinate of Gx for any X belongs to X. Coordinate of X is equal to summation of index of G in Gx, where C denotes the subset of X containing exactly the element from each orbit. We have coordinate of xg is equal to index of g in gx. Hence, coordinate of xg is equal to coordinate of g divides coordinate of gx, and hence coordinate of g is equal to coordinate of xg into coordinate of gx. Let C denote the subset of X containing exactly one element from each orbit of X under G. Then coordinate of X is equal to summation of Xg. X belongs to C. Since X is equal to union of Xg, X belongs to C, and this union is a disjoint union, and therefore coordinate of xg is equal to index of g in gx. Therefore coordinate of x is equal to summation of index of g in gx. This follows that tools of determining the numbers of orbit in a g set x under g. Next one, Bernstein theorem. Bernstein theorem. Theorem starting statement of theorem. Let G be a finite group and X be a finite G set. If R is the number of orbit in X under G, then prove that R multiply coordinate of G is equal to summation of coordinate of Xg for G belongs to G. For proof, let n is equal to number of order pairs xg belongs to x cross g. For each xg is equal to x, then for a fixed g belongs to g, there are coordinate of xg with pair with g as a second member and xg is equal to x. Hence, n is equal to summation of coordinate of xg. G belongs to G. Similarly, for a fixed row x belongs to x, there are coordinate of gx pairs with x as a first numbers and xg is equal to x. Hence, n is equal to summation of gx for x belongs to x. From these two conditions, summation of xg is equal to summation of gx is equal to summation of coordinate of g divides coordinate of xg is equal to coordinate of xg summation of 1 divides coordinate of xg for x belongs to x. Now let O1 O2 dot OR be R orbit of x under G. Then x is equal to union of OI, I is equal to 1 to R. This union is disjoint, hence we get 1 upon coordinate of xg is equal to summation of 1 upon coordinate of xg. x belongs to union of y, I is equal to I is equal to summation of 1 upon xg, x belongs to x, and a plus summation of 1 upon xg plus dot 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 plus summation of 1 upon xg. Hence now consider summation of 1 upon xg. Let O1 is equal to t1 t2 dot 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 tn, and therefore 1 upon coordinate of xg is equal to 1 upon coordinate of t1g plus 1 upon coordinate of t2g plus dot 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 plus 1 upon coordinate of tng is equal to 1 upon coordinate of O1 plus 1 upon coordinate of O2 dot 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 is equal to 1 upon n plus 1 upon n plus dot dot n upon n is equal to 1. Generalizing this theorem result, we get 1 upon coordinate of xg summation over x belongs to y is equal to 1. 1 plus 1 plus dot 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 r times 1 is equal to r. Therefore, 1 upon coordinate of xg is equal to coordinate of g into r. Therefore, r into coordinate of g is equal to summation of xg. G belongs to g, and this is